move on to celebrity talks. So our first prize winner is a PhD poster. Let me check. Jacob Luhn. He's talking about interesting discoveries when he studied noise in the data. He found some useful physics information in that noise. And for some people it's noise, for others it's treasures. That's what we hear today. Jacob, maybe introduce yourself, which stage of your PhD studies you are.
Right, can everybody hear me? You can all hear me? Okay. Right, so I am just finished up my third year at Penn State University, where I'm a graduate student, where I've been working with both Fabienne Bastien and Jason Wright. We're looking at astrophysical insights into radial velocity jitter. I want to first thank the organizing committees for putting together a great conference and for giving me this opportunity to speak today. I'll preface my talk by first saying that I'm coming at this from an exoplanet perspective. And so this conference has been especially a helpful learning tool for me, and I've taken a lot away from it. So I'll do my best to pitch this talk to both the exoplanet people in the room and all of the stellar people in the room. I also want to apologize for anyone who was in this room on Tuesday and heard Fabienne's talk. She did a fantastic job advertising my work, so if anything sounds familiar, that would be why. All right, I doubt that I need to go into too much detail here about what's going on, but for a long time, if you wanted to find an exoplanet, the main way you did this was to monitor the radial velocities of stars, looking for periodic shifts in the absorption features that indicate the gravitational tug of a planet. We heard the other day from Jesse Dotson about the transformative role that the Kepler spacecraft has played and continues to play and will continue to play in both exoplanet community and the stellar community. And in the exoplanet community, we're now in what I call the transit era, where the vast majority of our planets are discovered via the transit method. And in this era, radial velocities have taken on an additional role, and that is of transit follow-up. And we can use this to confirm or reject planet candidates, as well as estimate planet densities for these planets that we confirm. But with this additional role comes additional strain on our radial velocity resources. And there are simply more stars than we can reasonably follow up. And so we need better methods to prioritize targets and select targets for our radial velocity follow-up. And to do this, we can use the fact that some stars are simply intrinsically better suited for radial velocity follow-up than others. And that brings me to radial velocity jitter. So for the purposes of this talk, when I say radial velocity jitter, I'm referring to any scatter in the radial velocity time series, the RMS, that's induced by stellar variability. And I've broken these into two main categories: those that are driven by magnetic activity, such as star spots and flares, and those that are driven by convection, such as granulation and stellar oscillations. Historically, a lot of the past studies of radial velocity jitter have focused on the magnetic activity side of things, almost to the extent where activity and jitter are used incorrectly as synonyms, and only more recently have studies begun to understand the role that convection plays. As a quick aside, this talk was adapted from one that I gave at an exoplanet conference a little over a month ago, and looking through, I noticed that my exoplanet perspective is showing a little bit here with this term stellar noise, and I'll talk more about that in a bit. To summarize a lot of research in one sentence, more active stars have higher RV jitter. And this is just one example plot where we see that as stars increase in activity to the right, they also increase in this radial velocity jitter. The interpretation here is that more active stars are more likely to have star spots or faculae on their surface that, as we've heard, locally suppress convection, and then this is going to affect our disk-integrated radial velocity that we measure for the star. On the convection side of things, we've seen more recently, here's a plot from Fabienne, one of her papers, where we saw that more evolved stars also have higher radial velocity jitter. And so you can see here we're measuring evolution by the surface gravity, so more evolved stars are to the right, and you can see this increase in jitter. The interpretation here is that as stars evolve, both their granulation power and the stellar oscillation amplitudes are both increasing. And so this is again going to affect the disk-integrated radial velocity that we measure for the star. So my work has been focused on better determining which stars have jitter that's driven by activity and which stars have jitter that's driven by convection. And so I'll skip over a lot of the details of actually going through calculating radial velocity jitter for these stars and jump into the results. So what I'm showing here is on the y-axis this radial velocity jitter, radial velocity RMS that I've calculated for a sample of over 650 California planet search stars. And I'm showing again as a function of surface gravity, so more evolved stars are to the right. And now I'm color coding these points by their activity index measured by the Mount Wilson S index. So more active stars are in yellow and the inactive stars are in purple. To help guide you one step further, I've grouped these by their general evolutionary stage, so main sequence, subgiants, and giants. So from this plot, we see two very distinct features, the first of which is this vertical pileup of active main sequence stars. And these are stars at high surface gravities near their zero-age main sequence surface gravities for these stars. The other feature that we notice is this nearly horizontal pileup of inactive stars that show an increase in jitter with evolution. And so essentially here what I've identified are these two regimes, and so I'm empirically showing here this regime of activity-dominated and this regime of convection-dominated jitter. And this, again, as I said earlier, to the exoplanet community would probably be viewed as the stellar noise that we wish to get rid of, but for this study, this is the exact signal that we're looking for, and so we have to deal with something that we've been calling planetary noise, where the presence of planets will artificially inflate the measured stellar jitter that we wish to study. So astrophysically, then, what is this plot telling us? In a short sentence, it's that RV jitter is tracking stellar evolution. And what do I mean by that? So a star starts off, it's born, it's rapidly rotating, and it's very active, and then it's therefore jittery, with this jitter dominated by the activity. As it evolves on the main sequence, it gives off stellar winds, spins down, and decreases in both activity and jitter. It continues to fall in the jitter until it reaches some jitter minimum, where it transitions from activity-dominated to convection-dominated, where there's a gradual increase as it continues to evolve from convection. And so this sample here is a powerful tool in both communities. For the exoplanet community, you can clearly see how we can identify stars that will have low radial velocity jitter, and we can use this to predict the amplitude of this radial velocity jitter for a wide range of stars. Additionally, we can not only say something about the amplitude of RV jitter, but we can also talk about what's driving this jitter. And that's going to be incredibly helpful for planning observations of stars so that we can better mitigate, in this case, the stellar noise. On the stellar side of things, we can see here that these precision radial velocity measurements that we have can be another means of studying stellar evolution. And this will be incredibly useful then as we get these more and more precise radial velocity spectrographs coming online, and it'll provide a rich source of data for everyone. So I'll just quickly then end with these final points that I've made. I didn't have time to go through everything that I've I've done in this work. I have a paper that will be hopefully coming soon, so stay tuned for that. I'm also happy to take any questions. So, thank you.
Thank you very much. Very exemplary talk, very clear message. Questions? One here and there.
Heather Seglet, Geneva Observatory. So what you're showing for the main sequence stars makes sense because we know that young stars are more active. But out of curiosity, do you happen to actually have ages for any of your systems?
Yes. So, well, I haven't looked in a while at how precise they are. So we're simply using the updated stellar parameters from John Brewer's work, and I think in that he provides, I think, some isochrone ages, but he would have a better knowledge of that. I think that's what they are, so I don't remember quite how precise they are.
All right, next question is just right there.
No, thanks. I had the same question.
Okay, wonderful. More questions? One here, yes.
Chris Tinney from UNSW. So for most of our potential radial velocity target stars, we won't have the vertical axis on your diagram there a priori. So have you got any suggestions on how we use the information we do have to say which objects are going to be lying on that bottom floor there and not everywhere else in that diagram?
I missed the beginning part of that. Could you repeat that again?
Well, essentially, for all the Doppler observations and transit follow-up, we want to be targeting the stars in that bottom area there,
right.
And we don't know the vertical RMS a priori. So are there metrics that we can use to reject all of the objects except the ones on your bottom line there?
Right, okay. Yes, that's something that we're working on and will be part of, I think, if not this paper, then a follow-up paper. At least for the most part, you can see that the S index is a fairly good way to get rid of a lot of those, that vertical portion. So continuing to target these inactive stars is probably on first order the best way to do that.
One can probably look at photometric variability as well, if there is an observation of that.
Right.
Because that could be, higher velocity changes could be imprinted in some other variabilities. Okay, next question.
I just wanted to add to what you just said, which is if you have the photometry, actually the surface gravity can be obtained from the granulation noise in the photometry. So you could do both if you have precision photometry, figure out which stars are, and I guess that's where you're going to get them from because you're getting them from TESS or whatever. So I think this all does fall into a good scheme.
Yep, perfect. We're aligned. All right, thanks again. Let's